Hello, I am Neeraj Kumar. In this part of the tutorial, I will try to explain how you can design a quantum deep learning system by using quantum gates, by using quantum circuits, qubits, and external classical data. But to properly understand this tutorial, you should have background knowledge of qubit system, quantum philosophies, quantum circuit, quantum gates. Otherwise, it will be tough to understand this tutorial. I also uploaded some videos which explain all the prerequisites that I described here. Now, let us start with the architecture first, flow architecture first. Then we will go through that how we can achieve each part discussed in this flow architecture through with the help of quantum circuit or quantum deep learning system. So first of all, there is a classical data. So once we take the classical data, we need some encoding because the entire quantum deep learning architecture runs on some circuit, not like the classical deep learning architecture. So in this case, we convert the classical data into qubit encoding. And once we convert the data into qubit encoding, we pass it through parameterized quantum circuit. We say it parameterized quantum circuit because we use some set of parameters and weight which actually learns during the training process. The next phase is the output. So the parameterized quantum circuit generates the output, and the nature of the output is stochastic. That's why we can use that output to generate the epochs like we use in the classical deep learning architecture. So we use the output and pass it through the loss function. The loss function generally gives like information. The loss function will give the information like how far we are from the actual prediction results. Once we get the loss value, we use it in the gradient computation. The main thing which makes any classical deep learning architecture successful is the way we calculate the gradient. In a classical deep learning architecture, we use two main methods to compute the gradient. The first is by using some differentiation rule that we apply to calculate the gradient that we use in backpropagation. And second is auto differentiation. But the traditional way to compute the gradation is more famous. After that, with the help of those gradients, we get the parameter theta, which we require to update the parameter theta and other weights in the parameterized quantum circuit. And after that, we continue this in this loop until we get the required accuracy or we achieve the targeted minimum loss. So this is the way a quantum deep learning architecture actually works. Now suppose someone says that we have data like x is equal to 0, 1, 0, 1. Now you have a 4 qubit system like this. So all are in 0 state. So how you will pass this data? So the one method is, during my earlier lecture I described that there is a flip gate that is known as X gate. So here it is 0, so it doesn't require, but here we can apply the X gate. So it will flip the value 0 to 1. Here it is again not required. Here we apply the flip gate. But you will say that such kind of binary kind of numbers or bits we can get in very few data types or image data type or some things. But generally we get the data like this. X is equal to 0.5, x is equal to 0.6, x is equal to minus 0.7, x is equal to 0.9, like this. Then how your system will work? This is just a basic system. So for that we use the amplitude notation, or amplitude encoding. Several times it is known as angle encoding, angle-based encoding. So how angle-based encoding is working? Now, instead of doing this, we will use some rotation gate. Suppose we have one rotation gate which rotates around z-axis. We pass the value 0.5 for the rotation angle as a rotation angle, 0.6 as a rotation angle, minus 0.7 as a rotation angle, RZ 0.9 as a rotation angle. So actually what happens, we use some block sphere concept. Block sphere concept shows that in a sphere how we can differently measure the angle, and based on those angles related measurements we convert the data into a particular angle. I am not covering the block sphere related discussion here, because if we consider this, then it will consume the entire one tutorial. So I will discuss it separately in another tutorial. So just for working information, I have given that how much angle portions covered by different angle value that we use in the angle shift operations through angle shift gate. Now let us assume that our data is in the format like x is equal to x1, x2, x3, x4 instead of that decimal or something. So this will help in easily explaining the concepts. So what we will do in designing the encoding. Earlier I had just explained that how we can convert the data. Now we will design the complete encoding architecture. So first we pass the architecture through Hadamard gate. Do you know what is Hadamard gate? In earlier tutorial I had explained that how Hadamard gate is used to generate the superposition. So now it is in the superposition state. Now the next task is to convert our input qubit to this number. So what we will do, suppose we take the rotation angle RZ, x1, RZ, x2, RZ, x3 and RZ, x4. So this is rotation complete. Now we have a superposition and we have data conversion ready. Now what will be the next? Generally what happens when we write the traditional deep learning architecture like I1, I2, I3, I4 and pass it through some hidden layer, we just pass like this. Again for this we pass like this. So how we can achieve this kind of thing here? So for that we use the concept of entanglement. So how we can do that? So let us try. Now, how we can achieve the entanglement? In the previous tutorial, I said we will use C0 gate to achieve the entanglement, and we achieve the entanglement through like this. This is a control, this is a target, and just go and revise the previous lecture. You will understand things. So here, what we will do? Suppose we like I1 and I4, we try to just create the entanglement. Then what I will do, I will just take one entanglement like this. Okay, and after entanglement we generally do some operations. What operations we do? We change its angle, because most of the operations are reversible in the nature, and with this kind of change with the angle, we can properly map. And you will see that when I change the angle, we will not use the angle like this, because we are entangling x1 and x2, x4. So our change will represent x1 dot x4. So this is our change of angle. Now we will do one more entanglement here, and just after entanglement we will change its rotation. So rotation will change through, suppose, z axis. You can use y axis also, x axis also. So here it will be x1 x3, x1 dot x3. So be careful when you are doing planning entanglement like this. Now the next entanglement we can plan like this, and again we will change the rz x1 dot x2. So these are the changes. So after that there will be another gate, page operation shift gate. Now after this entanglement, I have just connected this to this. Now we can do some more connections, like we can connect this to this, and then we can again apply the entanglement rz. What will be the entanglement angle? We are connecting 2 to 4, so x2 dot x4. Now we take another entanglement, here to here. What will be the angle change? That will be rz x2 dot x3. We can do one more entanglement. That will be just like this. So this is another entanglement. Here again I will change rz x3 dot x4. So this is another gate. This is another gate. This is another gate, and the data will go. So this complete part is actually known as, so complete part, this complete part is known as encoding. We can apply multiple stacks of encoding also, and we can represent this encoding like suppose we have we can represent it like ux. Now we will pass the data to parameterized quantum circuit with parameter theta. So now how we can achieve that? So once we get all four output from encoding layer or encoding block, we apply some angle shift. Suppose we are shifting it through. Suppose we are shifting the angle through theta 1. Again for ry with respect to y axis, theta 2, ry, theta 3, ry, theta 4. So these are another angle change blocks. And once we achieve all the angle changes, we can propose some entanglements. So again we will go for entanglements. Why we are going for entanglements? Because in the traditional architecture, between the hidden layers, we are managing so many connections like this, that, this connection. So similar kind of connections, if you want to achieve in this architecture, then you have to apply entanglement, and this is the only possibilities. So what you will do, entangle this with this, means entangle this with this, entangle this with this. Again after that we can entangle this with this, entangle this. Again we can apply one entanglement like this. Now this is our parameterized quantum circuit block. One more thing, so it is like parameterized quantum circuit. This is block 1, like we said, block 1, like B1. We can add multiple such blocks here, like that. So as you increase the number of blocks in parameterized quantum circuit, you will have a capacity in your network to learn more feature depth and feature quality in your network. Even the way I described the parameterized quantum circuit is a very simple and basic one. You can use all different quantum gates to design a more powerful kind of network here. So now, suppose we represent it as W theta. Now, each of those gates will return some output. We already said those output will be stochastic in nature. Now, suppose you are doing some binary classifier. In this case, if you have 4 qubit architecture, then you will have 16 states in your outcome. So by using this 16 state to just apply a binary classifier will be little troublesome. So you can use one easy step. What kind of easy step we will do? So our easy step will be, we will just neglect this. We can see the highest entanglement or combinations, means this last qubit is more interacted with each other. So we will consider this only, and we can pass this, and then it will finally generate our output. Binary output with due to parameter theta, and it will be useless, means we will not use this. So based on the value of this, we can easily assign single value based on the value that we get from the last qubit. We can easily identify whether it will go with 0 class or 1 class. Now the next part is to compute the loss function, because we already get this, and then gradient also. Here loss function computation is very simple, and it is just like it may be just like a computation of similarity or differences, and even you can use some classical quantum deep learning architecture's loss function here also with very little changes. So now let us focus more on gradient. Yeah, hello. We had cut this tutorial for some time because I was just preparing this diagram to calculate the gradient. Actually, in the gradient computation, we generally use the parameter shift rule. This is known parameter shift rule. So why we call So instead of taking the differentiation or taking the derivatives, we just add a small parameters with this weight part and then compute the outcome, and again we subtract the small parameter s with this given parameter and then compute the output, and with the output from both cases, difference in output of both cases, we compute the gradients, and based on the gradients we identify that what may be the possible value to be updated for each of the parameters in the parameterized quantum circuit. So why we call it a parameter shift rule? Because we are shifting a parameter from plus s to minus s and take the differences. So this is very easy to understand. Now after that we continue the loop until we get our learning or training target. So now you understand that it is so easy to design a traditional quantum deep learning circuit architecture. You can use it for binary classifier, multi-class classifier, multi-level classifier. You can use it for regression also. So this is the basic concept here. In the next tutorial, I will try to explain how we can design the quantum CNN architecture.